So, thank you. So we can begin from where I stopped last time. So I want to talk about the Jacobi over relaxation. So the Jacobi over relaxation iteration method. So the Jacobi over relaxation. Or sometimes they write it like this. An iteration method for solving linear system of the form AX equals to B. So you find that it's just a case of the Jacobi method, iterative method. So it's basically, you find that we introduce a parameter that, so you find that we have a parameter omega, and you find that our xi now k, which is now part of our solution that we are looking for this, is written that that's just like an element in this column matrix. So it's written in that form, whereby this is the Jacobi update. Jacobi update, it's the one that we was updating like the new value in the Jacobi method. This one is just like scaling factor in this case, while this one just keeps part of the old value xk. Xk is like the previous value before we can get the new value. So you find that the general iterative form can be this. The general iterative form can be that, whereby here you're solving with the full matrix, not just part of the entries in the xk in the new matrix. Here you just get entries, while here you get the entire matrix at once. Now since we are just solving with the Jacobian, this is supposed to be D, the diagonal matrix. Now the first thing we want to, now let's see how we can write this in that form. So we know that from A equals to D minus N, then my N equals to D minus A. Can substitute this, therefore it can be written in that form, and this is also the same as I minus D inverse A. Now this is xk. Now I can categorize the ones which have xk together. So we categorize the ones which have xk together. Then we see that this and this cancel. So therefore we remain with, so we have it in the general form now. So this is k plus 1. So therefore this part here is equal to B GOR, just to mean, you remember we have several cases. We have the Jacobi case, we have this case, the Jacobi over relaxation case, and we also have the Gauss CIDL case with it, the successive over relaxation case. So that's why I'm trying to separate that this is B for this case and that is BF for that case, because you're always going to have those ones. Okay, so we can also go on and show that this system is consistent, this iterative method. So we have earlier seen that in the previous video, that first, to show that the iterative method is consistent, then we just have to use the fixed point equation. So I'll just use the fixed, so I use the fixed point equation in that way, written in that way, where x bar is the exact value of the exact solution. So I just want to show that this reduces to, that fixed point equation reduces to ax bar equals to b. So what you do is that, so this is what we have, substitute, I've just substituted. So I carry the one with x bar this other side, I take it this side. So when it crosses, this will be x bar minus this can be x that plus this is omega d inverse A of x that equals to W d inverse B. So these two cancel. So what do I remain with? I remain with omega d inverse A equals to omega d inverse B. So what do I get? So we see that these can cancel that. So therefore it simplifies to my Ax equals to B. So meaning that, so therefore my iterative method is consistent. Just like that.